Watch this yellow particle as a wave pulse travels the string. The pulse moves left to right, but the particle moves strictly up and down. This defines the mechanism of a mechanical wave. It is a disturbance that transfers energy continuously across space without causing a net transport of matter. The string stays exactly where it is, only the energy moves. To do this, mechanical waves require an elastic material medium, like water, air, or this string, to carry that energy. This is distinct from electromagnetic waves, like light, which propagate through a pure vacuum. Inside a physical medium, a passing wave forces particles to oscillate around a fixed mean position. They execute this motion in one of two distinct geometric patterns. The first is a transverse wave, where particle vibration is perpendicular to the direction the wave travels, creating alternating crests and troughs. The second is a longitudinal wave. In this case, particle vibration runs parallel to the wave's propagation. Instead of crests and troughs, this motion creates alternating zones of compression and rarefaction within the medium itself. To understand how the universe uses these oscillations to transfer energy, we must look past the physical motion of a single particle and build a mathematical blueprint that connects local vibration to macroscopic travel. This equation is the mathematical blueprint for a progressive wave. It details exactly how energy travels through a system. Y represents the exact displacement of a particle at any specific position x and any specific moment in time t. A determines the maximum amplitude of that displacement. Inside the sine function, the blue terms represent the spatial domain. K is the wave number, defined as 2 pi over lambda. It measures how many radians cycle per meter of distance. The red terms represent the temporal domain. Omega is the angular frequency, defined as 2 pi times frequency. It measures how many radians cycle per second of time. These spatial and temporal domains are linked by wave speed, which equals frequency multiplied by wavelength. Because of the relationships defined by k and omega, wave speed is mathematically identical to the ratio of angular frequency to wave number. This progressive equation is a rigid, dual-axis map proving that wave propagation requires both space and time to unfold. A governing rule of this math is that wave speed is completely independent of the wave's amplitude or the frequency of its oscillation. Velocity is exclusively determined by the inherent properties of the medium. It is the ratio of the medium's elastic restoring force to its resistance to acceleration, or inertia. For transverse waves on a string, wave speed equals the square root of tension over mass per unit length. Increasing the tension, the elastic component, speeds the wave up. Increasing the linear density, the inertial component, slows it down. The same logic applies to longitudinal sound waves. Here, the bulk modulus provides the elastic restoring force, and the density of the material acts as the inertial brake. When calculating the speed of sound in air, we apply Laplace's correction to account for thermodynamic pressure changes. The physical composition of a given medium acts as a strict, unyielding speed limit for energy propagation through that material. When a traveling wave pulse hits a solid vertical wall, it rebounds in the opposite direction. But notice its orientation. Reflecting off a rigid boundary forces a 180-degree phase reversal, causing the wave to invert entirely. If that boundary were free to move, the reflection would occur with zero phase change, and the wave would return upright. This visualization shows what happens when reflected traveling waves begin to overlap with incoming traveling waves. They obey the principle of superposition. The resultant displacement of the medium is the algebraic sum of the individual wave displacements. When waves meet in phase, they create constructive interference, doubling their amplitude. When they meet exactly out of phase, they create destructive interference, and their amplitudes cancel to zero. These overlapping waves do not destroy one another. Their energies superimpose, laying the groundwork for complex stationary vibrations. Through the continuous superposition of two identical waves traveling in opposite directions, a standing wave emerges. In the equation for this standing wave, the spatial component, kx, and temporal component, omega t, are no longer locked together. They are split into isolated sine and cosine functions. Because the spatial envelope described by sine kx is mathematically fixed, a standing wave no longer transfers energy from one point to another. It creates nodes. points of permanent zero displacement and zero amplitude, spaced exactly half a wavelength apart. Between these nodes are the antinodes, the points of maximum displacement. On a string tied at both ends, the physical boundaries force nodes to exist at the absolute edges of the medium. This constraint restricts the string to allowed wavelengths, where the length L must accommodate an integer number of half wavelengths. Because L must be an integer multiple of lambda over 2 to keep the end stationary, the string can only resonate at specific frequencies. This geometric requirement proves that a fixed string supports all integer harmonics. Boundaries effectively trap traveling energy, converting continuous wave propagation into a system of localized, quantized resonances. These same harmonic principles apply to longitudinal standing waves trapped inside columns of air. Open organ pipes feature free boundaries at both ends. This forces antinodes at the openings, allowing the pipe to generate all harmonic frequencies. Closed organ pipes feature a rigid boundary at one end, creating a node. This restricts the geometry so that only odd harmonics, the first, third, and fifth, can survive inside the column. These equations dictate instrument construction. Variations in pipe length directly command the fundamental frequency produced by shifting the physical boundaries of the standing wave. The physical geometry of an acoustic instrument is a rigid boundary constraint executing algebraic wave mechanics. Beyond spatial superposition, we must consider what happens when two waves traveling in the same direction share the same space, but have slightly different frequencies. This creates beats, a pulsing amplitude packet caused by alternating moments of constructive and destructive interference over time. The beat frequency formula shows that the beat rate is exactly equal to the absolute difference between the two source frequencies. Musicians utilize this mathematical phenomenon, listening for the frequency of the beats to precisely tune unknown pitches on their instruments until the interference disappears. Mechanical waves represent an elegant decoupling of energy from matter. They are an exchange of momentum governed entirely by the elasticity and inertia of the medium they travel through. From the fundamental pitch of an organ pipe to the interference beats of a tuning fork, all physical vibrations are the algebra of overlapping sine waves, adhering to the physical limits of their environment.